Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to the class on Bioclimatic Architecture, Futureproofing with Simple and Advanced Passive Strategies. Today we will have a look at the passive strategies that must be adopted in composite climate. First we will start with understanding what does the Mahoney's table say about the design and planning considerations for composite climate. According to the Mahoney's table, the planning should be compact courtyard planning. Then it should have a compact layout of the estates. The rooms should be double banked with temporary provision for air movement, and most of the times air movement is not a requirement. Opening should be medium. There should be heavy external as well as internal walls. The roof should be heavy with a time lag of 8 hours. There must be space for outdoor sleeping required. So this is what Mahoney's table says. Now let us see how to use climate consultant for a composite climate to arrive at appropriate design strategies, passive strategies as well as active strategies. So we will see for New Delhi, which is representative of composite climate for the month of March, which are the best strategies. By itself, 47.3% of the hours is comfortable in this place for this climate type. Sun shading of windows will make this place comfortable by 29.6% for the month of March. So there are 31 days in March. 31 into 24 is 744 hours for the month of March, out of which 220 hours will become comfortable with solar shading of windows. High thermal mass with night flushing will make 172 hours comfortable. Then we can adapt comfort ventilation, which will make 32.4% of the hours shift from uncomfortable to comfortable. Then internal heat gain, which will shift the comfort hours by 22%. And passive solar direct gain high mass will shift 16.1% of the hours or 120 hours to comfortable range from uncomfortable range. So, because of just passive strategies, 98% of the hours for the month of March can become comfortable by following simple and active passive strategies. Now, in order to make all the 100% hours comfortable, what should we do? So, there are these three strategies which are active strategies and the remaining are passive strategies. So, these active strategies would include dehumidification of air that will shift 5.5% hours to become 41% of the hours to become comfortable. 0.4% of the month or 3 hours can be made comfortable with cooling and dehumidification, whereas 1 hour will be made uncomfortable by heating and humidification if needed. So these are the three active strategies to ensure that 100% of the hours becomes comfortable. Then how can this be done for the month of March? A whole house fan or natural ventilation can store nighttime cooling in high mass interior surfaces, and using the concept of night flushing, we can reduce or eliminate the air conditioning load. Then this is one of the more comfortable months, so shade to prevent overheating, open to breezes, we can prevent solar gain, or we can have solar gain as per our requirement. Good natural ventilation can reduce or eliminate air conditioning in warm weather if windows are well shaded and oriented to prevailing breeze directions. Also, we should shade the western facade by means of shading devices or vegetation. Both of these will help to shade the walls, especially the western wall through which maximum solar radiation may enter. On hot days, ceiling fan can be used, which can reduce the temperature by 2.8 degree centigrade, and therefore less air conditioning is needed. The best high mass wall uses exterior insulation and exposes the mass on the interior, or we can add plaster or direct contact drywall. Let us see for the month of June in New Delhi, which is representative of composite climate, what happens if we use only passive strategies. Now 0.7 hours of the month is comfortable by itself, which is 5 hours. Solar shading of windows can make 36.9 hours or 266 hours to become comfortable. High mass night flushing is not an effective method, whereas adaptive comfort ventilation can shift 4.6 hours or 33 hours into comfortable zone from uncomfortable. So these are the only three effective passive strategies accounting for only 5% of the total month to be comfortable with the help of passive strategies. So in June, only 5% of the month will be effective with passive strategy. So in order to make the other hours also comfortable for June, we have to use active strategy, and those active strategies are dehumidification, which will cause 3.9 hours to shift to comfort zone. So 29 hours will become comfortable, and 91% of the month will become comfortable with cooling and added dehumidification. That is 655 hours out of 720 hours need air conditioning for the month of June in New Delhi, which is a composite climate. So, what are these strategies which we can use for the month of June? What are these passive strategies and the active strategies? So, use plant materials like bushes, trees, ivy covered walls, especially on the west, to minimize heat gain. If summer rains support native plant growth. Next strategy is use window overhangs designed for this latitude or operable sunshades or awnings that extend in summer so that the wall does not have any solar radiation falling on it, or the wall is protected from solar radiation. So protection of solar radiation is important. We can have double pane high performance glazing on west, north and east, but clear on south for maximum passive solar gain. On hot days, ceiling fan or indoor air motion could probably reduce the indoor temperature by up to 2.8 degrees centigrade, and so you may need lesser hours of air conditioning. But in general, we have seen that you require air conditioning for the month of June without fail. Let us see what happens in the month of September for New Delhi composite climate and the month of September. So none of the hours are comfortable by itself in the month of September. Whereas we can have sun shading of windows that can make 31.7% hours comfortable or 228 hours to be comfortable. Adaptive comfort ventilation can make 50.8 hours of the month or 366 hours comfortable. So totally 50.8% of comfortable hours can be done by using these selected passive strategies. So these are the passive strategies at the most that can be applied, making the indoors comfortable by 41% of the hours. But in order to make the room 100% comfortable, you need to have active means, and the active means is dehumidification, which has about 10% of the hours or 69 hours to shift from uncomfortable to comfortable zone. Then we have cooling and air conditioning, which is 47% of the hours or 339 hours require air conditioning to make the indoors comfortable. So these two strategies are needed in the month of September to make the indoors comfortable. So what are these strategies that we must adopt for the month of September for a composite climate like New Delhi? We should have screened porches and patios that can provide passive comfort cooling by ventilation in warm weather and prevent insect problems. We must have good natural ventilation which can reduce or eliminate air conditioning in warm weather if the windows are well shaded and oriented to catch the prevailing breeze. We should use plant materials like bushes, trees, ivy covered walls, especially on the west, to minimize heat gain if summer rains support native plant growth. Also, shaded outdoor buffer zones such as porch, patio, lanai oriented to the prevailing breezes can extend living and working areas in warm weather or humid climate. In order to produce stack ventilation, even when wind speeds are low, we should maximize vertical height between air inlet and air outlet like open store wells, two-story spaces, roof monitors, etc. Normally, this is a comfortable climate, so shade to prevent overheating, open to breezes in summer and using passive solar gain in winter will be very helpful. Let us see what are the strategies to be used in the month of December in New Delhi, which is representative of a composite climate. In the month of December, 14.9% or 111 hours are comfortable by itself. 1.2% or 9 hours can be made comfortable by solar shading of windows. Adaptive comfort ventilation can make the indoors comfortable by about 14% or 103 hours. Also, internal heat gain can make the indoors comfortable by 46.6% of the total hours or 347 hours out of 744 hours. 744 hours comes from 31 days in December into 24 hours, which is 744 hours. Then 38.4 hours or 286 hours out of 744 can make the indoors comfortable with passive solar direct gain high mass. So just by using passive techniques, you can have 81.7% of the hours or 608 hours out of 744 hours of the month to be comfortable by adopting only passive strategies. And the remaining 18% will still remain uncomfortable for the month of December unless you adapt some active strategy. What is that active strategy? That active strategy is dehumidification, which can be applied for 2 hours of the month. Then 18% or 134 hours can become comfortable if you use heating with added humidification. So active techniques which include heating and humidification can make 18% to become comfortable, making the total 100% of the month to become comfortable. So what are these strategies? So heat gain from light, people and equipment will greatly reduce heating needs. So we should keep the home very tight and well insulated in December. For passive solar heating phase, most of the glass area on the south must be exposed to maximize winter sun exposure, but we should design overhangs to fully shade it in summer. We can use high mass interior surfaces like slab floors, high mass walls and a stone fireplace to store winter passive heat and summer nighttime cooling. Sunny, wind-protected outdoor spaces can extend living areas in cool weather, such as enclosed patios or sunrooms or courtyards or verandas. Trees must be neither coniferous or deciduous, and they should not be planted in front of the wall. The front of the wall should always be exposed and in such a way that solar radiation will fall on it and prevent the shadow of the trees to fall on the wall. So this prevention, in order to prevent that, the trees should be planted beyond 45 degrees from the wall. Organize floor plans so winter sun penetrates into daytime, making the indoors warm. Now let us compare the various strategies and what is its impact for these various months. So comfort achieved using passive strategies, 98% of the March month can be made comfortable just with passive strategy. Whereas for the month of June, 5% can be made comfortable with passive strategy. In September, 51% of the month can be made comfortable with passive strategy. Whereas in December, 82% of the month can become comfortable only with passive strategy. What are these strategies? Adaptive thermal comfort ventilation can be used for the month of March and September. It must not be used in the month of June and December. Whereas internal heat gain should be used only in the month of December. Sun shading of windows is a good strategy for March and September, whereas adaptive comfort ventilation can be used only in June and passive direct solar gain with high mass can be used only in December. In March, we can use high thermal mass night flushed, and this must not be used in June and September, but adaptive comfort ventilation can be used for the month of December. Internal heat gain can be used in March, not in the month of June. In the month of December, this can be supported with sun shading of windows. Passive direct solar gain from high mass can be used in March as well as in December, but not for the month of June and September. So you can see for a composite climate, there are a variety of strategies strewn over the months. So it becomes very important for you as an architect to prioritize or have that strategy which can be operated in such a way that that strategy can be used only for some months and need not be used for the other months. So you can even design some of these strategies yourself, because composite is one of those slightly complex climate where you require all these strategies but in various months. In order to make the indoors 100% comfortable, so for the month of March, 2% has to be made comfortable, and that comes from humidification, cooling and dehumidification, heating and humidification if needed. Whereas cooling and dehumidification is needed for the month of June and September. But in December, heating and humidification is needed. For all the 3 months, June, September and December, dehumidification alone can also shift some hours from uncomfortable to comfortable hours. So this is how you understand the strategies that can be adopted for a composite climate. We will see how this is done in the further course of this lecture. First is building orientation. You need to minimize the surface to volume ratio and minimize the perimeter to area ratio. So you should increase compactness by reducing the surface area for the same volume as we had already seen in the previous classes. Second is how to use shading devices. So self shades through massing results in cutting off of a large amount of direct radiation. So we had seen in the previous class also how we had seen in the much previous classes how self shading can act as a strategy to reduce the impact of solar radiation. So understanding solar angle is important in designing the shading devices. Third is use of shading devices. So horizontal shading devices are suited to southern exposure roof overhangs can also be easily used to shade the southern exposure on low-rise buildings. So, this is perhaps the most economic and potentially aesthetically pleasing solution. Vertical shading is beneficial for the sides of the building that get direct sunlight during specific times of the day. East facing sides receive morning sun and west facing sides receive afternoon sun. Vertical shading elements such as vertical fins, screens or vegetation can block the lower angle sun, reducing glare and still allowing natural light to enter. Courtyards are another feature that can be used in this climate. So, due to the incident of radiation in a courtyard, the air gets warmer and rises. Cool air from the bottom level flows through the louvered openings of rooms surrounding a courtyard, thus producing air flows. At night, the nice and cozy roof surfaces get cooled by convection and radiation. The next strategy that can be used in this climate is jali. So, jalis on the outer facade of the building helps in cooling, shading and ventilation. These jalis, when used outside, also serve as a double wall and at the same time allows ventilation inside, cuts the solar radiation and keeps the indoors cooler during the hot part of the year. So, here you can see how jalis can be used in different ways. Next is evaporative cooling. So, water is a good modifier of microclimate and water features a moderating effect on the air temperature of the microclimate. It possesses a very high thermal storage capacity, much higher than the building materials like brick, concrete and stone. So, water can be used for two reasons. One is for evaporative cooling and the second function is to increase the air humidity during the hot and dry period. During the hot and dry period, increase the air humidity because the humidity can get reduced even up to 30%, making the air extremely dry, especially with a combination of extremely high temperature. So, water body can serve as a evaporative cooling effect and normally a combination of courtyard plus water body works best. Then thermal insulation is another strategy to prevent heat gain due to high thermal mass. You can have thermal insulation or have the building envelope comprised of high thermal mass. So, having insulation is one strategy and the second strategy is to have a high thermal mass. During daytime, heat gain through solar radiation, occupants, equipments inside is stored in the thermal mass. Concrete slab, precast ceiling panels, heavy weight mass walls can add thermal mass to buildings. Traditionally, thermal mass was added with the use of mud walls. For night cooling, water or outside air is passed through the building at night to carry the heat stored in the thermal mass during daytime. So, thermal mass can be used with night cooling or cooling the buildings passively. Diurnal swing, that is the difference between daytime and nighttime outdoor temperature, must be high for thermal mass to be an effective passive cooling and heating strategy. The next strategy that can be used in this climate is wind tower. So, in a wind tower, the hot air enters the tower through the openings in the tower, gets cooled, and this becomes heavier and sinks down. The inlet and outlet of rooms induce cool air movement. In the presence of wind, air is cooled more effectively and flows faster down the tower and into the living or habitable space. After a whole day of air exchanges, the tower becomes warm in the evenings. During the night, cooler ambient air comes in contact with the bottom of the tower through the rooms. The tower wall absorbs heat during daytime and releases it at night, warming the cool night air in the tower. The next strategy we can use is passive downdraft evaporative cooling. In this system, wind catchers guide outside air over water-filled pots, inducing evaporation and causing a big drop in temperature before the air enters the inside. Similar wind catchers come as the primary rudiments of the architectural form as well. The next strategy is cool roofs. So, cool roofs are roofs which are covered with a reflective coating that has high emissivity property, which is very effective in reflecting the solar radiation away from the roof surface. This quality greatly helps in reducing the cooling load that needs to be met by the HVAC system. Combination of insulated roof with cool roofs has high saving energy potential. Thermal emittance like re-radiation of absorbed heat and solar reflectance, that is solar energy reflected back of cool roofs, is very much higher than conventional roofs, which enables them to prevent solar radiation from being passed on to the interior of the building. Then roof pond is another strategy. The roof pond system requires a body of water to be located in the roof, which is protected and controlled by external movable insulation. This body of water is exposed to direct solar gain, which absorbs and stores this heat. Roofs should also be properly insulated so as to minimize the heat transfer from the roof to the inside of the building. Provision of adequate rainwater drainage is also essential in this climate. Next is natural ventilation. The orientation of the openings is determined by the ability to utilize the cooling effect of the breeze prevailing during the warm humid season and to utilize the heat of the sun during the cold season to cut off the ventilation during the cold part. So, one must be very prudent while using this strategy in composite wall, because when the strategy is used for one climate type, it can become adverse during the other climate type. If the strategy of natural ventilation is used during the warm humid period, it can become adverse during the hot dry period and vice versa. The next strategy is the earth air tunnel. So, using the passive cooling effect of ground, this device can lower the air temperature in the air duct by even up to 10.6 degrees centigrade. Due to rocky terrain of site location, this technique cannot be used. Next is green roof. So, stormwater runoff reduction happens when we use green roof. Solar radiation intensity gets reduced inside the building. Thermal heat gain gets reduced. Energy consumption gets reduced. Impact on urban heat island is reduced. Green roofs can even improve the air quality, provide sound insulation. It can improve roof materials longevity, and also we get additional area for plantation of produce. So, green roof can be another strategy for enhancing indoor thermal performance. Then we look at green wall as a strategy. The next strategy we use can be vegetation. So trees and shrubs, they create different airflow patterns, providing shading and keeping the surroundings cooler during the warm weather. Vegetation can be used for energy conservation in buildings by shading of buildings and open spaces through landscaping, providing roof gardens or green roofs, shading of vertical and horizontal surfaces like green walls, buffering against cold and hot winds, changing direction of wind, etc. So, vegetation is a crucial element in altering the microclimate of an area. It can prevent reflected light from carrying heat into the building from the ground or other surfaces. Additionally, the shade created by trees reduces air temperature of the microclimate along the building through evapotranspiration. Providing deciduous trees on the southern side of a building is useful in a composite climate. So, today we have seen passive design strategies and advanced passive design strategies for designing in the composite climate. We saw that the suggestive softwares give strategies for overall throughout the year strategies as well as during the crucial periods of the year. As an architect, use your discretion to follow which strategies must be used. Also, understand which strategies must be modified before using. Some case studies where these strategies have been applied in the composite climate. The first one is the CII Sorabji Godrej building in Hyderabad. So, the CII Sorabji Godrej Green Business Center in Hyderabad is a LEED rated platinum building in India. It offers advisory services to the industry in the areas of green building, energy efficiency, water management, environmental management, renewable energy, green business incubation and climate change activities. An office building built over 4.5 acres of site for about 2000 meters square. It's a commercial office building and scored very high in LEED rating of 56 out of 60 in those days. So, the campus is located in high and financial district of Hyderabad in close vicinity to Google, Oracle and Deloitte. The site is surrounded with medium-rise commercial buildings. The location is also near landmarks like Shilparamam and High-Tech Exhibition Center. The site gives a premier advantage to the employees by being near the location of residential zone of Kothaguda and High-Tech City. It's an ideal zone for campus planning. It is located on the flattest zone on site with least interference to site features during construction. It has easy access from main road, is centrally located on site, has scope to create buffers surrounding the building for effective design according to site climate. And this building is less prone to pollution. Let us look at the site plan. The site plan shows that there is a water body in the building on account of its topography, and closer to that is the designed root zone treatment plant. This site is covered with a lot of vegetation. The concept of this design is based on the Pancha Mahabhutas, which is an ancient belief that states life exists because of the presence and balance of 5 classical elements. They are associated with the 5 senses. They act as the gross medium for the experience of sensations. Amongst these are the use of materials, being energy efficient, enhancing natural ventilation, provision for renewable energy, socio-cultural response of the site, having a good water management system, concept of sustainability with reuse and recycle, and lower carbon footprint. So the plan is closed formation of concentric spaces with courtyard in the middle. The plan is derived from subtractive combination of several built spaces and green pockets. The arrangement of spaces is radial. Similarly, the structure is also radial. The structural formation is derived from circular arrangement of columns and slanted combination of radial beams. The building has a semi-open circulation through public and semi-public spaces. The pattern of circulation is in two forms, radial and circular, merging to complete the free and open flow throughout the building. The spaces are vastly open to give maximum exterior green views. The elements that are used in this building, which aid as a climate responsive element and also as a simple and advanced passive strategy. These are: first is a courtyard. A central courtyard and colonnaded corridors ensures that the hot air cools before entering the interiors. The courtyard also acts as the area for interaction. The plants collectively create a space of diffused light that just adds more to the liveliness. Second is use of traditional elements. The walls are commonly experimented feature in aesthetics with several arrangement and patterns. The walls allow a controlled flow of air and light into the interior space. Jalis used to prevent glare and heat gain while ensuring adequate daylighting. The jali walls increases the surface area and mass of the facade to cool much of the breeze in the passage. The third is use of glazing for lighting. Now the courtyard itself is a large light well which spreads light coming from the top. The 20,000 square foot building is designed around a courtyard, a traditional gathering space for intellectual encounters, cultural functions, and social interactions, which act as a light well, providing light to the adjoining rooms. It helps in stack ventilation and forms a safe inside yet outside environment. The natural light from the courtyard combined with energy efficient lighting systems results in 88% energy savings, higher than that of an electricity lit building of the same size. Around 90% of the building spaces have daylight access and views to the outside. The north facades are fully glazed for efficient natural lights. Low heat transmitting glass has been used. Double glass to further reduce heat gain has been used. Double glazed units with argon gas lighting in between the glass panes also enhances the thermal properties. The building design and layout itself ensures that 90% of the spaces have daylight access and views outside. The north facades are glazed for efficient diffused light. Low heat transmitting glass have been used, and these double glass also double up to further reduce heat gain. Natural lighting has been used and no lights are used until late in the evening. Light captured from as many sides as possible and also the courtyards help in having the rooms being lit with maximum natural light. Next is water management. Now, conservation of water was of prime concern for this project. Here, they have used the root zone treatment plant, which helps in two ways. One is in the waste management of the sewage as well as water conservation. So, water generated in the building is treated with root zone treatment plant, which is a process to treat wastewater through a biological mechanism. The treated water is used for irrigation requirements within the campus. The CII Godrej building campus has achieved 56 lead points, and a key aspect of this is because of zero discharge of water, which is aided by the green roofs among other features. All the wastewater and runoff generated by the building is recycled by root zone treatment, which you would have seen in the site plan located in the lowermost area of the site. This has specially selected plants which purify and filter the water that irrigates them. Water leaving the root zone treatment is directed to one of the three ponds, thereafter to be used for domestic purposes. The building achieves a 35% reduction of municipality supplied potable water, in part through the use of low flush toilets as well as waterless urinals. Rainwater harvesting is another important criteria. Some rainwater goes into the soil with the use of grid pavers used on roads for easy drainage of water. The remaining rainwater follows existing flow patterns and is collected in the water pond. Wastewater is treated with the help of root zone treatment, and the treated water is also used for watering the landscape and also for light and low flush toilets with waterless urinals. The next aspect is of ventilation through wind towers. So, two air cooling towers are erected where air is cooled up to 8 degrees by sprinkling water. This cool air is circulated inside the building, minimizing the load on air conditioning. The wind tower is connected to the AHUs, substantially reducing the load on the air conditioning system. Due to the unpredictable wind direction, opening on all four sides are provided with an additional effect due to the wind pressure. The next component is the terrace gardens. So 55% of the roof is covered with terrace garden, helping to reduce the interior temperatures. 20% of the building energy requirements are catered to by solar photovoltaics. The solar PV has an installed capacity of 23.5 kilowatts. Vertical landscaping has been used in certain areas and is an essential feature of this building. It has been used as facade element while some has been used as partition element. Vertical landscaping is an influential element to enhance the vibrance of green buildings. Apart from aesthetics, these act as additional mass to the wall and reduces the heat load in the building. Next, uses of materials and resources. 80% of the building materials have a large proportion of post-consumer or post-industrial recycled content. The masonry construction has a considerable content of fly ash, which is an industrial waste. The walls are constructed using fly ash blocks and fly ash cement. The ceramic tiles used for flooring have cullets, broken tiles, papers, etc. Instead of conventional ply or wood, the project used a composite agro board manufactured from bagasse, which is a sugarcane waste. Local and regional materials have also been used, and 95% of the materials used in the project were harvested, extracted, or manufactured within the radius of 500 miles. 65% walls are constructed with fly ash bricks, which feature a cost reduction of 20% less than traditional clay bricks which are normally used. These are lighter than clay bricks, have high strength, practically no breakage during transport, and have high recycled content. Bagasse board is a byproduct of sugarcane industry. It is low cost and durable. It has wide usage for making partitions, furnitures, etc. Waste management plan ensures that 95% of construction waste was recycled. Further, some industrial wastes like broken glass, broken tiles, broken stone, recycled paper, recycled aluminum has also been used. The next important feature is the indoor air quality. Indoor air quality is continuously monitored and minimum fresh air is pumped into the conditioned spaces at all times. Fresh air is also drawn into the building through the wind towers. The use of low volatile organic compound paints and coatings, adhesives, sealants and carpets also helps to improve indoor air quality. Hydrofluorocarbon indicates that the refrigerant is comprised of hydrogen, fluorine and carbon. HFC refrigerant gases are considered to be more environmentally friendly because they are the third generation of fluorinated refrigerant gases. They were developed to be more environmentally friendly, definitive alternative to CFC and HCFC. Other notable green features are the, the fenestration maximized on the northern side, use of rainwater harvesting, using waterless urinals in men's restroom, having water efficient fixtures which are ultra low and low flow flush fixtures, having HFC based refrigerant in chillers, having energy efficient lighting systems through compact fluorescent light bulbs, have large vegetative open spaces, have swales for stormwater collection, maximum daylighting, have operable windows and lighting controls for better daylighting and views, have electrical vehicle for staff use and shaded car park. So, the CII Godrej has tried to use many simple passive systems as well as advanced passive systems suitable for their climate and also other features which has got them the LEED Platinum rated certification. We will quickly see another case study which is PIDA, Punjab Energy Development Agency, which is an office complex in Chandigarh. So, PIDA Chandigarh is a state nodal agency responsible for development of new and renewable energy and non-conventional energy in the state of Punjab. This is a solar passive complex in Chandigarh by architect Arvind Krishnan. It's a 5-star rated building under Bureau of Energy Efficiency star rating of government building schemes. This project aimed at demonstrating an architectural design developed in response to elements of nature, which is sun, wind, light, and utilization of solar passive systems. The context of the site analysis shows that the building design needs to respond to a composite climate context of the site, and the final design solution needed to satisfy the diverse and often conflicting conditions of the hot dry, hot humid, temperate and cold period of Chandigarh. So, the climatic conditions were 2 months of hot dry, 2 months of hot humid, 2 months of cold period, occasionally hazy sky with hot winds in summer, low humidity in summer, high in monsoon, cold winds in winter and strong winds in the monsoon. So, the strategies required were cooling in the hot dry period, natural ventilation in the hot humid period, heating in the cold period. Cooling remains as the predominant requirement since the total overheated period extends from mid-April to mid-August. The orientation of the building became an important simple passive technique to be considered. So, the building has a three-dimensional form responding to solar geometry, that is minimizing solar heat gain in hot dry period and maximizing solar heat gain in the cold period. The site is minimal in size and the building is the result of the shape of the site. It was therefore not possible to orient the building in a specific direction. The entire facade of the complex has used different strategies to reduce heat gain during the summer. The design of the building envelope reduces the effect of the external atmospheric conditions on the interior spaces. The central atrium of the complex is covered by a lightweight hyperbolic shell roofing of 10 centimeters of high density extruded polystyrene, which is sandwiched between high grade fiber reinforced plastic sheets, and it is reinforced with steel. Daylighting has been used with the help of atrium, which has been specifically angled to allow the sun in during winters and block it in the summers, only admitting in glare and heat free daylight. The hyperbolic shell roof is coupled with solar panels sandwiched between two sheets of toughened glass, which not only generate electricity but at the same time let diffuse daylight into the central atrium. The concrete domes structured on the southwest facade are one of the well recognized innovations of this project. These domes have horizontal and vertical intersecting fins with glass fixed in the voids. These voids allow natural light with reduced glare. The shading action of the fins allows indirect sunshine to enter the building in summers and direct sunshine in winters. Cutouts in the slabs make it possible for this natural light to reach multiple floors. Next is ventilation. The water element consists of water bodies and fountains. Fountains are operational during hot and dry months, that is April to June, and help decrease the interior temperature through direct evaporative cooling. The wind tower has a mechanical component, that is the ambienter, and uses the method of indirect evaporative cooling in which water cools the air without coming into contact with it. Solar chimneys have been used and placed atop the light walls. These are used to expel hot air from within the building. In turn, fresh air rushes in from the openings in the envelope, passes over the floor, heats up and escapes through the lower top. Insulation has been used. The walls are made up of two layers of bricks with a 5 centimeter air gap in between. These cavity walls in the southern and western facades have insulation consisting of 60 centimeter by 60 centimeter panels of 6 centimeter thick rock wool wrapped in polyurethane sheets. These have been placed between the layers of bricks in addition to the air gap. The combination of a brick wall with air gap reduces heat transfer by 50% as compared to a conventional brick wall. If insulation is added along with the air gap, the heat transfer decreases by 85%. The atrium roof is a central hyperbolic shell roof with 10 centimeter of high density extruded polystyrene sandwiched between high grade fiber reinforced plastic sheets. The concrete roof, a maximum heat gain is through the roof. A rock wool and polystyrene insulation with an air gap of 5 centimeter from the concrete slab has been placed. Top layer is made of mud fusca and brick tiles for further heat proofing. So if you see, the overall building looks like this. It has a series of advanced passive strategies like use of solar chimney, use of light wells, use of solar PV panels, having a wind tower. So, I am not going into the description of what is a wind tower and a solar chimney because we have done it for so many of our previous case studies. So, the PIDA building demonstrates a great example of a passively designed building in a composite climate. Numerous passive strategies such as southern dome structure, water bodies, wall insulation, having double walls or rather having cavity walls have been used and complemented by some other strategies, advanced strategies like wind tower, solar panels, etc. The design of the building is equally as important as the passive strategies applied for them to work well. The open plan of this building makes it possible for the benefits of the passive and active strategies to be useful throughout the building. The integrated PV solar panels placed on top of the atrium roof produces 25 kilowatt power to meet the basic electric requirements of the office. So this PIDA office has a EPI, Energy Performance Index, of 14 kilowatt hour per meter square per year, which is one amongst the lowest in the country in the category of non-air conditioned buildings. For a perspective, the EPI of commercial building is above 180 kilowatt hour per meter square per year, and the benchmark set by BEE for buildings compliant with ECBC 2007 is 140 kilowatt hour per meter square per year. This itself shows it's an energy efficient building. So, today we saw case studies of buildings which are designed for climate responsiveness in composite climate.